Hi there, welcome to Data Science Explorer. This is the Data Science interview series, and today we'll talk about cross-validation. After this tutorial, you will be able to answer what is cross-validation, why do we use cross-validation, what are the different types, choosing the right cross-validation technique, what is the workflow, and lastly, a hands-on example on implementing cross-validation techniques in Python. Let's dive in. What is cross-validation? Let's understand the fundamental concept. Simply put, cross-validation is a statistical technique used to assess how well a machine learning model will generalize on unseen data. It involves partitioning the data set into training and testing subsets and iteratively evaluating the model's performance on these subsets. By doing so, cross-validation provides a more robust estimate of the model's performance compared to a single train test split. Traditionally, we split our input data into train and test in a ratio of 80:20, 70:30, and so on. What this does is it takes in a random block of test data and trains the data on the remaining chunk. Data trained in such ways might create a model that performs really well on this data set, but on unseen data, it might generate either a good production model or a bad production model. And also, it does not necessarily that the model always performs in the same way always. On implementing cross-validation to train a model, this helps in segmenting the data into multiple train and test splits for each iteration, thereby capturing the different data trends and patterns within each fold and generating an accuracy for each of these models. Then picking the model which generalizes our data set better helps us in generating a model that is more stable in production. Why do we need cross-validation? You might wonder why is cross-validation so important. There are so many several advantages that makes this a very valuable tool in our machine learning world. Robust evaluation. Firstly, cross-validation provides a more reliable evaluation of our model's performance. By using multiple subsets of data, we reduce the impact of data variability and obtain a more accurate estimate of how our model will perform on unseen data. Optimal use of data. Secondly, cross-validation allows us to make most efficient use of our available data. Rather than splitting our dataset into just a training and test set, we can use different combinations of data for training and evaluation, maximizing the information we extract from our dataset. Model selection and hyperparameter tuning. Thirdly, cross-validation helps us compare and select the best model amongst different alternatives. By evaluating each model's performance across multiple folds, we can choose the one that generalizes the best and achieves the highest accuracy. On improving generalization, the model will help on predicting well on unseen data, thus reducing overfitting. There are different types of cross-validation techniques, the first one being Holdout Method. This is the simplest form of cross-validation. It involves splitting our data set into a training set and a separate validation or a test set. While straightforward, this might not be suitable for smaller data sets due to limited data availability for both training and evaluation. K-fold cross-validation. This is the most popular technique. This divides our dataset into k equally sized folds, where generally k is 5 or 10. We then train our model on k-1 folds and evaluate on the remaining 1 fold. This process is repeated k times, with each fold serving as the validation set once. Stratified k-fold cross-validation. Stratified k-fold cross-validation is particularly useful when dealing with imbalanced datasets. where the class distribution is uneven. This ensures that each fold maintains a representative distribution of classes, allowing us to obtain more reliable evaluation metrics. Leave one out cross-validation. This takes the idea of k-fold cross-validation to the extreme. It uses each data point as a validation set and trains the model on remaining data. This type of cross-validation provides an unbiased estimate of our model's performance but can be computationally expensive. Repeated k-fold cross-validation. For even more robust evaluation, we have the option of using repeated k-fold. This involves performing k-fold cross-validation multiple times with different random partitions of data. This technique provides a more reliable average performance estimate across multiple runs. Choosing the right cross-validation technique. The holdout method is suitable when you have a large dataset and computational resources are limited. However, it might not be the best choice if the dataset is small because you might end up with insufficient data for training or evaluation. K-fold is common and suitable for most scenarios and strikes a good balance between model evaluation and efficient use of data. If your dataset is large, k-fold cross-validation is generally the reliable choice. K is generally 5 or 10, but you can experiment with different values depending upon the size of your dataset. Stratified k-fold cross-validation is useful when dealing with imbalanced datasets, where the class distribution is uneven. It ensures that each fold maintains the same class distribution as the original dataset. This technique is beneficial when accurate representation of minority classes is crucial. Leave one out cross-validation provides an unbiased estimate of model performance but can be computationally expensive, especially for large datasets. Repeated k-fold is used when the dataset is small or the model's performance is sensitive to data partitioning. Cross-validation workflow. First, we split the data into input features and target variables. Then we choose a suitable cross-validation technique based on the data characteristics and objectives of our dataset. Next, we implement the chosen technique using libraries like scikit-learn and TensorFlow. Train the model on the training set and evaluate its performance on the validation set. Next, we repeat the training and evaluation process for each fold or iteration. Finally, an average performance metric across all folds and iterations are calculated. Next, let us move on to a hands-on example of implementing cross-validation in Python. We use the iris flower classification dataset to perform cross-validation. First, we import all the libraries that we need like pandas, sklearn model selection. We train the model using support vector machines. We read the dataset using pandas into a pandas data frame and then check to see if the load was successful. Here we see an extra additional ID column has been generated, which we would be dropping in the next step. We then split the data frame into X and Y, X denoting all the input predictors that we would use like sepal length, sepal width, petal length and petal width, and Y being the target variable which we use to classify the species. We then create the support vector machines model using a linear kernel and then define the number of folds as 5. First, we perform a k-fold cross-validation where we define the number of splits as 5. We do a shuffling of our data and we set a random state to 42 just to ensure that we are able to reproduce our outputs. The scores are computed and for each fold, the accuracy of our model varies. What we see for fold 1 and fold 2 is a 100% accurate classification of our flowers, whereas fold 3, 4 and 5 we see the accuracy dropping. If in the traditional way of splitting the data into 80-20 or a 70-30 split, we might have a chance of taking in the first model of correctly classifying all the data sets. But on deploying this model into production on unseen data, it might not have been able to generalize the data patterns well and might not be able to generate an accuracy as good as 100%. Next, we do a stratified k-fold cross-validation, and recalling earlier that this is k-fold cross-validation but ensuring that the class balance is maintained within each fold. We split the train and tests and then fit the model on the training part. We then compute the accuracy scores and we see that the accuracies for 4 of these models are 100%, whereas one model it is 93%. These models in turn perform better than the regular K-fold models because we ensure there's a class balance maintaining in each of these folds. By conducting this exercise, we understand that a straightforward train and test split might not generate a very reliable production model, but by performing cross-validation and picking the model that best replicates our data patterns helps in building a model that is more reliable on data that is unseen.